Is it visible?
Yes, it's visible. Yeah, go ahead.
Okay. So good evening, everyone. So here we are into another paper reading session. So this paper is by Daniel Gregory, and it is about distinguishing ore deposit types and barren sedimentary pyrite using LAICPMS uh, and using the trace element data to get the deposit type of pyrites. So we will speak a bit about the author. This is Daniel Gregory. He is an assistant professor in the of economic geology at the University of Toronto, Canada. He has previously worked as an exploration geologist, and he got his PhD from the Center for Ore Deposits and Earth Sciences in Australia. He got his postdoc at CODES and at the NASA Astrobiology Institute in UCR. He used in situ analysis technology to understand the fluid involvement in ore deposit formations. Presently, he is testing machine learning to identify ore deposit types and vector towards economic mineralization. So that was all about the author.
Okay.
So let us.
I can insert a little bit about the journal and the author.
Sure.
The journal Economic Geology is a journal people publish about topics on economic geology. This journal has a lot of attention in the industry. So for example, for exploration, for companies, mineral resources exploration companies, they might read economic geology. But I don't think that they're going to read, like Earth and Planetary Science Letters. EPSL, I don't think that the companies are going to read that. So this paper actually fits that goal pretty well. So it talks a little bit of science, but a lot about the methods, because for the drilling process, because for the question of making quick decision in drilling process is one very hot topic in applying data science in geology right now. Actually, one of our collaborators, Huang Fang, from from Australia, who's currently working in Australia. Actually, he's also working on similar topic like this. So once you get the drilling core, you see certain compositions, then make the prediction model to see whether they should continue with the drilling or not. So this is a very good topic to work on. And then for Daniel Gregory, actually I didn't know that he does have exploration experience at Yukon territory. So Yukon is really in the north of Canada. So I know several people that have been explored Yukon before, and it's extremely beautiful wilderness. But people went there partly because of the mineral exploration, and also they have places for good natural samples, of course. And so for the postdoc position of the Gregory, Daniel that spent was at UC Riverside. He was working with Tim Lians. And so that he has got a lot of exposure in the sedimentary geochemistry community. So, okay, so I just talked a little bit about the journal and the author. So please move on.
Okay. Just a minute. Yeah. So the key, I'll just deal with the what I have tried to do in this paper while reading was that I tried to put in the essence of the paper. So the key points were that the paper aims to provide a classifier that will return the mineralization type of the pyrite mineral based on its trace element composition. So if you put in suppose if you give in the trace element composition of a pyrite sample as an input, you will get the deposit type. So how does that help in a real life world? So in most exploration scenarios, the near surface geochemistry or the structural features are not suitable to give us adequate information about the deposits which lie in depth or the deposit types. So for example, detrital pyrites can be assumed to come from a lot of deposit types, but each of these deposit types needs different kind of drilling equipments. So if there was a way in which we could know just by analyzing the near surface pyrites and classify them into what deposit this pyrite might have formed from, the drilling costs, the exploration cost, and all these costs go down. So this paper has that particular site in mind. Now, how does the trace element concentration versus the deposit style? The trace element concentration in pyrites can help us to approximate the composition of the fluids from which the mineral had precipitated, as well as the crystallization mechanism. Hence, this trace element data can be used to predict the deposit type the pyrite sample is associated with. We also know that different fluid sources result in different deposit types. So once we can analyze the fluid source from the pyrite, we can characterize the deposit style of the pyrite. In this context, one more thing that the paper or the work was successful in was like discriminating or distinguishing the pyrites that form in the sedimentary process from the pyrites that form in the hydrothermal process, that which can become a bit trickier uh, to distinguish under a microscope or just by petrological studies. So the data they had was around 3,579 data. Some of them were taken from previous works. Most of them were funded by, I don't remember which project funded it, but it was most of them were funded and they were analyzed in their own lab. But a major chunk was also taken from pre-published literatures. And what they did after this was they made a supervised classifier using the random forest algorithm. So you can see the data spread and the different types that they had taken into consideration. They have also mentioned a lot of ways, like obviously, like any other data-driven project, it includes data pre-processing, the classifier training, and the prediction evolution. So this paper, unlike the last papers we have gone through, or unlike most of the papers, they give a very detailed mechanism. Like if you are working with pyrite and you want to know how to pre-process your data, this paper is a go through. So if anyone is interested, it has a lot of writing on there, a lot of bits and bytes, so one can read through that. The LAICPMS data was mostly analyzed for cobalt, nickel, copper, zinc, arsenic, moly, silver, tellurium, and so on and so forth. And one more thing, so what they did was, one of the problems that one can face while doing a LAICPMS was the influence from the micro-inclusions of other minerals from while you are ablating or you are burning the burning the slide. So what they did was they, as far as I remember, this went through some zinc percentage and some cobalt percentage, and if these two percentages were more than 2% and 1% respectively, they discarded those data, citing that the influence from micro-inclusions were considerable and those data were not fit for their data set. So how the data was quite well distributed so that the skewness of the training data could have been reduced. So with exceptions of the VHMS and IOCG deposits, the number of analysis done in different type of deposits were taken as equal. The training data was hence safeguarded from being skewed to weight a particular deposit type owing to its abundance in the data set. So no particular data, no particular deposit type had more data compared to the other, apart from VHMS and IOCG. However, the geometric mean and the median of the training data set did establish that all the deposit types were equally represented, and hence even if there was a slight difference in the VHMS and IOCG numbers of and IOCG analysis, it was a balanced data set after all. So we can safely bet that the biasness of this data set was removed. So the result that we got, I took the snap from the picture itself with apart from writing. So you can see that the accuracy for different data types, different deposit types were different. So like we get an overall accuracy of 91.4%, but it's 94.9 for IOCG, 78.8 for orogenic gold, 81.8 for porphyry copper, and 93.6 from SEDEX. However, what they did was, so they tested the RFC, the random forest classifier, using data deposits, and the training data yielded a better accuracy. So you can see the changes in the picture. So overall, what was done, I think I have given, just I'll go to the last part to show this. So the overall accuracy of the test data and the blind test data were 94.5% and 93.9% respectively. And this was achieved from 91 when they reduced or they kicked away the inconclusive analysis from their data set. So again, this is the training data visualization. So the blue dots over here, they represent the IOCG deposits. The green stand for the orogenic gold, the yellow for the porphyry, the black dots or the pink, these violet ones, sorry, these violet ones are for the SEDEX. The yellow ones are for the sedimentary pyrite, and the red ones are for VHMS. So you can see how they all give a trend, like when you represent it against the trace element concentrations. But one thing that I had a doubt was that eventually they should form clusters, but I don't see any distinguishing clusters between them, but there's a lot of overlapping data. And there is no really any other picture or visualization given the paper that shows that how actually if I give data from different deposit types, I'll get clusters or proper classification. So the how the model gives the output that is not given in the paper, and I couldn't find it. So these were the trace elements that they took into consideration: cobalt, nickel, copper, zinc, arsenic, so on and so forth. One more thing that they did was, there was some, apart from this sources, if the pyrite came from some other sources like barren sources or barren pyrites, so they made a provision for that also, that in case the source was not from this, those pyrites were also separated. And that is all for this paper. What I have avoided, I can tell you that there's a lot of technicalities in how to model the random forest classifier, how to better optimize it. But I try to restrict myself into the fact that this is entirely the essence of the paper. So that's all. Now it's open for discussion if anyone has any questions or anything.
Okay, thank you, Arka, for leading the discussion. Okay, now it's time for us to ask some questions. Actually, a quick one. So what is the blood for the blind test samples? So where that's coming from? Probably I have not read the paper into that detail.
So are you asking about where the data came from?
Right? Yeah, the blind test data.
Yeah, so they have actually shared that. What I'll do is that I'll share a new screen. I have the PDF open. Okay. Just a minute. Can you see the PDF?
Yes, I can see.
So over here, actually the paper is very what it deals with, like the introduction and the results and conclusions are very less, but its methodology is very well explained. So I'll show you where it came from. They gave actually different tables for this. So this is the data set. This is the table 1. These are the data that they used for training, test and blind set. And over here, okay. So these are the papers that they used, but they didn't mention it separately, that which were taken for like over here, sorry. So you see the number of samples that they took for. So the blind test data are these papers. So it's not that from a single paper they took all the training, and the other papers they took it for tested. So they divided every paper. From every paper they took some training data, some test data, and some blind test data. So this is how they did it. So it's quite well accounted for.
Yeah, I don't know. Yeah, I don't know why they don't do the cross validation.
Actually, what the author, I can tell you one thing, that they have not given how their model actually works. They have given how you can optimize a random forest, how you can basically make the data set better, but how their particular model works, that is not so much visible in the paper. And what they have given is that they have given a provision that if anyone wants to work later, over here only, I'll show it to you. So Just
Uh,
so what did they say that they're like, if anyone wants to get the pyrite data analyzed, so they won't give the code, but you can give them the data and they will basically do the analysis in their model and give you back the results. So that is something they've given, but there was one paper where they've given the code basically, but it is not so in this case. And also there's no, I couldn't see like if they have classified it, like if there was classifications, like this models from this visualizations, what I can see is that the deposit types, they don't form, like especially uh, sedimentary pyrites, they are very much overlapping with the other pyrites. So how did they actually distinguish it based on the trace element concentration? Because they're not very distinct. It's not that we have very distinguishable clusters over here. So maybe if on tomorrow, if he shows that how the output, how the model finally looks like, it will be a bit more clearer.
yeah, but here does he has the feature importance result for the random forest?
No, I think because it's a multi-class classification, so maybe they didn't.
Okay, I see.
Yeah.
I see. Okay. I think
And
another thing is that the plotting log scale. I don't know whether if they don't play the plotting log scale, some of those yellow and some of the green dots might be more
So the
separated.
green are for the orogenic gold and the yellow are for the porphyry. So here is the key. So this is
I can see.
this is the
And for the cross-validation part, I have something to say that, and in this paper they used, they say they ran 10 times with different random selections, like they changed the random states, and it's kind of like the cross-validation, but I think it's not as stable as the cross-validation. So maybe they think they did something just like the cross validation.
Yeah, because what they have said is that they're justified that like one thing that what Ben said was they say that cross validation is basically while they're using the random forest, since it's an ensemble learning, so basically they use bagging technique. So it is kind of the algorithm itself validates the best set of data that like by permutation and combination of different sets of data, that which is the best result coming. So that is what they have said here. But again, there are people or there are models where we have seen that cross validation was used separately even while they're applying random forest. Maybe that's a reason what Ben said, that they have avoided using the cross validation.
Yeah.
Okay, then you could ask him tomorrow, I think.
Yeah, we can do
Okay.
that.
Okay.
Yeah.
And
Why they don't use that? Okay.
yeah, and I don't know the blend test if it's necessary, because they have test data set, and the blend test data set. I don't know whether it's is necessary, because there's two accuracy result in the conclusion, right? For the test part and the blend test part. So I don't know how they compare these two numbers. And by the way, they said they just split the data set into the train, test, and blend. They didn't see how they split it, how they select the blend data set. Yeah.
Yeah. I think it's a good thing to ask, because whether the blind test data could represent.
Yes.
Well, whether training data set, like I said, whether blind test data could represent the training data set is another thing.
Yeah.
So here is that the division that they used for how many, like what they used for training and test and what for blind data set they used. So the numbers are given over here.
Yeah, right. And the left up part you can see in this page, and yeah, just in last you just show the data distribution paragraph up they say the remaining 681 analysis from 27 different deposits formations were used as the blend test of the trained classifier. They just say that much about the blend data. So yeah, maybe they just select for some purpose, not the random, not the random. Yeah.
So Shichao set has the Gini values. What does that mean? Shichao.
You can see that as a important features, something somehow like that. So this plot shows the Gini distributions, the Gini values. Gray one, the bar plot.
Yeah.
There is a bar.
Yeah,
bar plot.
777 that page. Yeah, I don't know what.
So Arka, could you turn to that page?
77737.
Yeah, sure. Yes, they have given that graph over there, but yes, this is the thing. The Gini decrease with the elements, but
it's more like something like the important feature means if the value of this feature is high, means you can use this value to separate or classify the deposit as said in this paper. But if the value is low, means the this set should be pure, or means all the data should come from one type of the deposit. So it's somehow like the important features.
Okay.
Yeah, so what I understand is that they might have used this to shortlist that which trace elements to use. Like it's a kind of feature selection, right?
Yeah.
Yes.
Yeah, so they might have shortlisted the trace elements they need, but how could they actually discriminate between the deposit types? That is what Ben was asking, I believe.
I think they couldn't do it because obviously.
That's why I think that's why they show us the data visualization results.
Yeah. And
so they want to give us somehow the first one. The first one, maybe this one, we can use this one to classify or separate the to several multiple clusters in the result in the plot.
Yeah, but they also show us I think they also show us this element couldn't split the different class. You can see in the later figures that they use the elements versus elements those figures, and I think the first or second elements couldn't split them out.
No ideas. Maybe 2D plot is not enough for us to separate. Sometimes we may use 3D like the PC result.
Yeah, that's
So
true.
I'm still have these questions about the but for sure the Gini values is somehow can equal to the importance features means maybe maybe the mass transfer between different deposits is different, especially when we consider the PB element. That's maybe that's the meaning of that plot.
They have given something over here. Just let me scroll down. They have mentioned that this scatter plots can't be used, but then they have given this only. Like there's no other. What they have tried to show is that like it is not possible by a 2D visualization to differentiate them. Hence, their model is kind of fine. But there has to some kind of clustering that should occur in other dimensions, like in a 3-dimensional plot or something. Else, how can the classifier work?
Okay.
Like if you see over here, they have see this part.
Mm-hmm.
They have written that these scatter plots are not can't be used to distinguish.
Yeah, right.
But then they have not given any figures, other figures. So, and even their code is a black box.
Yes. Yeah, I think it's normal because even the feature importance can't you can't just like choose feature importance and try to classify the data, use these two elements. That just use two elements like something like that. So yeah.
Yeah, I agree with you. Like this selection of data, everything, their optimization seems very perfect. But then again, there's a lot of things that are not explained in this paper, or rather that are not shown in terms of figure in this paper. The theories are only given. So maybe tomorrow he will show a few figures, or we can ask him.
Yeah. Yeah, and I also want to ask him what's the point of the blind data set, because he has a task data set, right? Because when you get the task score, you just use the train to perform the task. Not the task has also not been trained, right? It's just like the task data, or task just like the blend. I don't know.
Yeah, I have this like say, he has a blind test. For example, Chen Hua's work that basically did have I won't call it a blind test, but it's a test with no result. I think these are convince the geologists better, I suppose.
Yes.
But I think this,
yeah.
But I don't think this is very sound from data science perspective.
Yeah.
What I mean is that I just Googled it. So basically, what I mean is that this blind data set basically stands for validation set. I believe that.
Yeah.
So he has a training set, he has a test set, and he has a validation set. So that sounds fine.
Yeah. That's right.
Maybe use different words, but it's strange still.
Yeah. Just use different words. But the problem is that how do you know that if the validation data set is a subgroup of your training and the test data set? because if the validation data set basically comes out of that, then basically it could not be applied.
Yes.
Or if the training data set is not a homogeneous distribution, and then, for example, if the data is more concentrated in area A, but less concentrated in area B and area C. So most of the training data in area A. And then when you have the blind data set, then most of the data in the blind data set could come from the data area B and C, and only with a small amount from area A. And if you do that, then it probably won't work very well. Maybe that's another way to tell whether the test data set is has been trained by the training data set. Maybe that's another way to tell. If it works, it's great. If not, then people could say, oh, the training data set doesn't cover that area. Okay. Do we have more comments, ideas? I think we have prepared several questions for the speakers tomorrow.
Yeah.
Okay. Thanks, Arka, again for leading discussion. And let's listen to what the speaker is talking about tomorrow. I think this paper is only part of his talk tomorrow. Here's something more to talk about by Kyle right here. Okay, have a good night.
Good night, everyone.
And in the Northern Hemisphere, it's the shortest night in this week of the year.
Yeah, I'll send you the slide.